All right, everybody. So what we are going to do now is go through the calculations to prove out what we saw in person when we mixed our silver nitrate and our potassium chromate solutions. So just as a reminder about the concentrations and the amounts that we added together, for the silver nitrate, we added 5 milliliters of silver nitrate, 0.1 molar. And then we added the same for our potassium chromate, 5 milliliters. And just as a reminder, the potassium chromate was a yellow color. So I'll just go ahead and make that yellow there. And when we mix those together in our test tube, obviously not drawn to scale here, we made a red precipitate, a red solid here. And then after we centrifuged it, what we saw was that we had some yellow solution that was left over. Okay. Now, the yellow solution visually lets us know that we have some potassium chromate solution that did not react. But in order to really understand why that is, we need to look at the calculations and look at exactly what happens when we mix these solutions together, look at what we call the complete ionic equation and then the net equation as well. All right. So when we mix these together, we had a silver nitrate solution. We had a potassium chromate solution. And when we mix these together, we have a double replacement reaction that happens. So the silver is going to react with the chromate, possibly and form a precipitate, and our potassium and our nitrate will possibly form a precipitate. Looking at your solubility rules, you're going to see that the nitrate ions are always soluble. So your nitrates are always soluble, as is your group 1 elements, which includes potassium. So these two are going to remain in solution. So you're going to have KNO3 that remain in solution. And the precipitate is going to be the silver chromate. And your formula for silver chromate is going to be Ag2CrO4. And since it's a precipitate, we'll label it as a solid. The silver ion is a +1 ion. The chromate ion is a 2- ion. And so that is the reason for our formula here. We need 2 silvers to balance out the charge of the chromate to make a neutral compound. Just to wrap things up here, we need to balance our equation, putting a 2 in front of the silver nitrate, and then also a 2 in front of the potassium nitrate solution. All right. So next, what we want to do is look at, so I would call this just sort of our normal, regular equation. We're going to look at something called the complete ionic equation. In our complete equation, instead of writing our solutions, our aqueous solutions together in a formula, we're going to recognize these actually exist as ions. And we'll do that for all of our aqueous solutions. So for silver nitrate, potassium chromate, and on the product side here for our potassium nitrate. So we want to recognize that the silver nitrate is made of silver ions. And we're going to distribute this too. And it's also made of the nitrate ions. Okay, so again, this 2 in front, this coefficient is distributing. Then what we have is our potassium chromate. So we have 2 potassium ions. And we have our chromate ion. Okay. Notice that I didn't write in the aqueous here. Most of the time it's understood that if you are dealing with something in the ion form like this, that it's aqueous. I'm mainly omitting it here just because of space reasons. On the product side, I'm going to write my KNO3, my potassium nitrate, as ions because, again, it's aqueous, distributing the 2 in front. And lastly, we come across our solid precipitate. And because this is really sort of changing form, we're going to keep this solid together when we write it. So we have Ag2CrO4 solid. So we keep that the same. So this is what's called the complete ionic equation. And what we do is anything that's aqueous, we write it as separate ions because that's really what's happening. Once we take to make this silver nitrate solution, we took the solid and dissolved it. And when it dissolved, we actually separated the ions from each other. So this is actually a more accurate way of describing it. So that's the complete ionic equation. Now what we would then do is look at something called the net ionic equation. And in the net equation, really focus on the things that are changing and reacting. And so a quick way of doing this is to really look at what's forming the precipitate. So we're going to keep our precipitate on the right-hand side, our product side. So this is our formula of our precipitate. And focus on what are the ions, what ions went together to make our precipitate. Well, it must have been the silver ion and the chromate ion. So what we do is we locate those ions in our equation. And we have the silver ions and we have the chromate ions. And this is our net ionic equation. Another way of thinking about this, and something that you might be asked to do, is look at these, what we call the spectator ions. And spectator ions are ions that are not changing form in any way. They're the same on both sides of the reaction. And our spectator ions, I'll highlight these in red since I wrote spectator ion in red, would be when they appear exactly the same on both sides. And you'll notice that we have our nitrate ions are the same on both sides. And also your potassium ions are the same on both sides. And so if you focus on what do we have left after we eliminate our spectator ions, we have our silver ions and our chromate ions and of course our precipitate. And that's how we come up with our net ionic equation. It's not to say that these ions aren't present in solution. They are. They're just not doing anything. They're remaining soluble and they are present in this this mixture of ions, this solution that we have left over. Okay. So what that leads us to then is a discussion of, well, why do we have some of these left? Because you'll notice that we use the same volume of solution and then we had the same concentration. So why do we have any excess reactants here? Well, the answer lies in the net ionic equation. In the net ionic equation, we recognize that in order to make this precipitate, you need 2 moles of silver ions to react with 1 mole of the chromate ions. And that's going to form 1 mole of our precipitate. So this is our equation, but it doesn't necessarily tell us what we actually mixed together. So what we now need to do is look at our how much we actually added. So we had 5 milliliters of a 0.1 molar silver nitrate solution. And then we also had 5 milliliters of a 0.1 molar potassium chromate solution. Now, after working with molarity for a while, you're going to probably naturally hone in on the fact that you've got a volume and you've got a molarity, so you can calculate how many moles that you have. And so when you rearrange your molarity equation, for moles, you're going to take molarity times your volume in liters. So plugging this in, your molarity is 0.1 molar. Your 5 milliliters is 0.005 liters. So our moles of silver nitrate that we have are going to be 5 times 10 to the minus 4 moles of silver nitrate. And it turns out that because we use the same volume and same concentration of our potassium chromate, the moles of potassium chromate that we have are the same because our volume is the same and our concentration is the same. So we have the same number of moles of potassium chromate. Now, to relate this back to our net ionic equation, we're not necessarily thinking about moles of silver nitrate, just moles of silver. And also the same, we're thinking about moles of the chromate ion instead of moles of the potassium chromate. So looking at the mole ratio, for every 1 mole of silver nitrate, you have 1 mole of silver ions. So we have, focusing on the silver ion, we have 5 times 10 to the minus 4th moles of silver. And similarly, in 1 mole of potassium chromate, you have 1 mole of chromate ions. So we have 5 times 10 to the minus 4th moles of chromate ions. So now that we know how many moles of silver ions and moles of chromate ions we have that we mix together, how did they react? Well, remember, our picture tells us that we had excess of our chromate solution. We know that because it was yellow. And the chromate solution is yellow. The silver nitrate is virtually colorless. So we know that this yellow must have come from excess potassium chromate. So how can we use these numbers here? Well, we basically know that we have excess chromate ions. So what we could do is figure out how many chromate ions you would actually need based upon your limiting reactant, which is our silver ion. So we could say if I have 5 times 10 to the minus 4th moles of silver ions, we could say how many moles of chromate ions would we need? We calculated how many we have, and we know that's more than we need. It's in excess, but we can calculate how many moles of chromate ions we would actually need. Now, just as a reminder, our net ionic equation looked like this. 2Ag plus CrO4 2 minus is going to produce Ag2CrO4 solid. So this tells us the mole ratio of silver ions to chromate ions, and that's what we're going to use to calculate this. So on the bottom, we need to have moles of silver ions from our equation. There are 2 moles of silver ions in our equation for every 1 mole of the chromate ion. So what we have next is to say, is do our calculation here, and we come up with 2.5 times 10 to the minus 4th moles of chromate ions that we actually need. So we need 2.5 times 10 to the minus 4th chromate ions, and we have way more than that. We have twice as much as what we need. So that's the reason that we saw visually that we had excess of the chromate solution. We have more of these chromate ions that haven't reacted. And what we did in the laboratory to verify that, we added more silver, which we had run out of. We added more silver, and we saw more precipitate form, confirming that, yes, we did have excess chromate ions. The next step after this that you might be asked to do and think about is what would be the concentration of our ions that do we have left in solution after the original reaction occurred. And that's a story for another lesson. Thanks for watching.